Hello and welcome to our lesson on factoring and GCFs. So this lesson, actually this whole module, is probably one of the most important that you're going to be learning in your mathematical career, particularly if you're going to continue on to college algebra and levels of math beyond that. It's just one of the concepts that occurs over and over throughout most of our algebra classes. So not to put any pressure on you, right? But it's possible you've had some experience with factoring before. If not, it's totally fine. I'm going to teach it like you've never seen it before. So what we're going to look at today is sort of the basics. Okay, it's like an introduction to factoring. What does it mean to factor? And then particularly what we're going to be looking at is the first step in any factoring process. So as we move throughout this module, we're going to look at different ways to factor different sized polynomials. So we'll use a different process for a polynomial with 2 terms versus 3 terms versus 4 terms. But no matter which of those processes we look at, the first step in any of them is going to be finding and factoring out what we call a greatest common factor, or a GCF. Okay, so before we get into that, what does it mean to factor? Do you have some concept in your head of what it means to factor? So basically what factoring is, it's the process of rewriting one polynomial as a product of 2 or more. It's you could think of it as the reverse of multiplying. So I want you to look at this example. If I gave you that example, and actually we looked at that in our first module, and I said to multiply that out, we know we would distribute. So we would multiply here, 2x squared times 3x squared is using our product rule, where we multiply those coefficients, 2 times 3 to make 6, and we add the exponents, so 2 and 2 makes x to the 4th. And then we multiply again here, use our product rule again here, so 2 times 5 would be 10, and we'd have x to the 2 plus 1, which would be 3 altogether. And then 2x squared times negative 4 is going to give us a negative 8 with just the x squared there. So if I was to start here and end here, that is our multiplying process. We looked at that again in our first module. What we're doing here is we're working in reverse. So instead of taking the 2 polynomials and multiplying to make 1, we are going to be starting with the 1 polynomial, and we have to work backward and figure out what 2 polynomials we multiplied to make that happen. So when we start here and work our way backward, when we start with 1 polynomial and rewrite it as a product of 2, that is factoring. That is what we call the factoring process. Okay? So it's taking 1 polynomial and rewriting it as a product of 2 or more polynomials, and you can also think about it as the reverse of our multiplying process, the reverse of multiplying polynomials. Okay, so again, as this can be a complicated topic, I'm going to hopefully break it down so that it's manageable for you. But there's a little bit of vocab we got to get into before we can actually start the factoring. Okay, so what does it mean to be a factor of a number or a variable? So if you're looking at 12, for instance, if I said, what are the factors of 12, could you tell me? Well, hopefully you're thinking of numbers like 1 and 2 and 3 and 4 and 6 and 12, because each of those divides in evenly. So a number or a variable, we'll get to that in a second, is a factor of another if it divides evenly into it. Okay, so it's a factor if it divides in evenly. So factors of 12, as I just mentioned, would be 1, because 1 divides in evenly, 2 and 3 and 4 and 6 and 12. All of those numbers divide in evenly, so those are all the factors of 12. I guess I should say not equals, but I should say factors. The factors include 1, 2, 3, 4, 6, and 12. Okay, now if it's a bigger number, excuse me, like 70, do you think you could as easily tell me just in a list there what all the factors of 70 were? I mean, maybe. It's possible that you miss a few, but the reason I ask is because I want you to be aware of a process to find all the factors if you can't just see them or list them out. So what is the process that we use to find all the factors if I can't just make a list off the top of my head? Well, we use a factor tree. So if I was to break this down using a factor tree, let's see, 2 goes in 35 times, and then 35 we could say is a product of 5 and 7, and then 2, 5, and 7 are all prime. So if I was going to list out the factors Obviously, 1's going to be a factor. It's a factor of everything. And then for my factor tree, I have what we call the prime factors. So I would include 2 and 5 and 7. And the prime factors help me find the other factors, the composite factors. So any combination of our prime factors multiplied is going to produce another factor. So for instance, if I multiply 2 and 5, I get 10. That means that 10 has to be another factor. Or if I multiply 5 and 7, I get 35. 35 has to be another factor. Or if I multiply 2 and 7, I get 14. 14 has to be another factor. Or if I multiply all three of these numbers, so the 2 and the 5 and the 7, right, I get 70, and obviously 70 has to be another factor. So if we really needed to, we could take a number, break it down, find the prime factors, and then any combination of those prime factors multiplied would produce another factor. So all of my factors of 70 would be 1, 2, 5, 7, 10, 14, 35, and 70. Okay? So that's not a process you're going to be doing all the time. For the most part, when you're looking for factors, you're going to be able to identify what you need. But I show that to you because it's helpful when you start to look at something that's a little more foreign, like these variables. Okay, so what are the factors, for example, of x to the third? It's kind of a weird thing to think about, right? Let me scooch this over a little bit. X to the third. It's a weird thing to think about. So what I would suggest is, well, let's break it down like we broke down the 70. What does x to the third really mean? Well, it really means that we're multiplying an x times an x times an x. So it's like the prime factors would be x, right? X to the first is the prime factor. So if I was going to make my list of factors here, I could definitely put x to the first on the list. And then any combination of those multiplied would produce another factor. So for example, if I multiply an x and an x, I get an, it's starting to look like marshmallow there. If I get an x squared, that's got to be another factor, right? Or, let me just, hang on. Why did I circle that? Let's just get rid of the comma. And let me just rewrite this. Okay, so x squared is another factor. Or if I multiplied all three of these, the x and the x and the x, then x to the third has to be another factor. Okay? So my factors of x cubed would be x, or x squared, or x cubed. Now, again, just think about this, make sense of this, okay? What it means for x and x squared and x cubed to be factors is that they divide in evenly, right? Just like 2 divides into 70, 5 divides into 70, 14 divides into 70. Does x cubed, does it divide evenly by x to the first? Because that's what we're saying. Well, yeah, it goes in exactly x squared times. Or does it divide by x squared? Yeah, it goes in exactly x to the first time. Or does it divide by x cubed? Yeah, x cubed divided by x cubed is exactly 1, right? So each of those things divides in evenly. Okay, let's try this again. If we had xy squared, that really means we have an x and a y and a y. So if I was going to list out the factors here, I could definitely put the prime factors of x by itself and y by itself, and then any combination of those would produce another factor. So x times y makes xy another factor. Or let's see, don't want that one. How about y times y? Y squared then has to be another factor. Or the whole thing, right? The x times the y means xy squared would have to be another factor. And then of course I could put 1 on both of those lists as well. Okay, so we can find factors, hopefully, of numbers and or variables. But the goal is to be able to look at not just one number at a time or not just one variable term at a time. It's to be able to look at a set of these things and determine what is the greatest common factor for that set of terms. So if I knew all the factors of 70 and all the factors of 12, I could say what's the greatest common factor? What's the biggest number on those lists that they have in common? Well, for 12 and 70, it's 2. Okay, so if I was looking at this list and this list, that's the biggest one that they have in common. So that would be the greatest common factor for 12 and 70. Okay, so I got to be able to find that greatest common factor for a whole set of terms. So what is the largest number and or variable that divides evenly into every single term in an entire polynomial? So if I was looking at, let's say, 27 and 18, do you know how to find the greatest common factor? Well, I could go about the factor tree thing, right? But we should be able to look at 27 and 18 and know what's the biggest number that divides evenly into both of those. Hopefully you can see it, right? Hopefully you can see the greatest common factor, GCF, for these two terms is going to be 9. 9's the biggest number that goes into 27 and 18. Now, if you couldn't see it, like maybe in the next example, we could use factor trees. So I could take the 54 and say 54 is 2 times 27, and then 27 becomes 3 times 9, and then 9 becomes 3 times 3. So let's see, break down the 84. Well, actually, let me finish what I'm doing with this one. So we have the prime factors of 54 being 2 times 3 times 3 times 3. Okay? And then let me break down the 84 here. So 84 would be 2 times 42. And then 42 would be 2 times 21. And then 21 would be 3 times 7. Okay? So here, my prime factors would be 2 times 2 times 3 times 7. If I can find all of the prime factors they have in common, then the product of those prime factors that they have in common will produce the greatest common factor. So what prime factors do they have in common? So if I was looking for what's the same on both of these lists, well, they both have a 2, and they both have a 3. Is there anything else that they have in common? Well, there's a 2 left over here, but not on the red list. There's a 3 left on the red list, but not on the green list. A 7 on the green list, but not on the red list. So what they have in common, their GCF here is going to be the product of the 2 and the 3, which is a 6. So the GCF here is 6. Okay. Now again, this isn't really work that you're going to be doing all the time. For the most part, it's going to be like the first one here, where you're looking at 27 and 18, knowing the biggest thing that goes into them is 9. However, your calculator or Desmos, the app I've had you download, will also do this for you. But the calculator or Desmos doesn't call it a GCF. It calls it a GCD because it's the greatest common divisor. It's the same concept, right? What's the biggest number that divides into a set of numbers? Oops. Here I meant to put GCF. Calculator can do the GCF, but it calls it GCD. Now, it won't be able to do this with variables, but it will be able to do this with numbers. So for example, oh, sorry, that's my college algebra mess. Let me delete that. If you go into Functions, Statistics, and then GCD. So over here it says Functions. Press that. Go to Statistics, and then down here GCD, not Statistics. Is it miscellaneous? Good grief, it's miscellaneous. Let me fix this. It's Functions, and then not Stats. It's miscellaneous, and then GCD. Okay, so let me start that over. Go to Functions, and then we want the Miscellaneous tab, and then GCD. So if we put in 54, 84, it tells us what we just found out, that the greatest common divisor for 54 and 84 is 6. So now we could use that again for this last one. If you wanted to make factor trees, you absolutely could, but hopefully now you can just use some technology to find the GCD. So again, let's go to Functions, Miscellaneous, GCD. What's the greatest common divisor, greatest common factor for 12 and 48 and 18? It's again 6. So in Desmos, we did this one. We did Desmos again to get a GCF of 6. Okay? Feel free to use the technology. That's why we have it, right? At this point in our math careers, I'm not testing if you can make a factor tree and circle some numbers in the factor tree. I want you to be able to use technology because we got to move past that a little more quickly than making all those factor trees. Although, this is where it's coming from, okay? So, we've got some examples with just numbers in there. Whoops. Let's look at some that contain some variables, okay? How do I find the greatest common divisor for a set of variables like x cubed and x to the 5th? Well, remember, we could do the tree thing, say x cubed is x times x times x, and x to the 5th is 1, 2, 3, 4, 5 of those being multiplied together. So if I was circling what do they have in common, well, they both have 1, 2, 3 x's in common. So here the GCF is going to be x to the 3rd power. Okay? Now, I don't know necessarily that that's something I want to be doing every time, although let me show you once more. X squared y would be 2 x's and a y. Xy to the fourth would be x and then 1, 2, 3, 4 y's. What's in common here? Let's see, they both have an x, they both have a y, and that's it. So here we're going to say the GCF is an x and a y. Now again, I don't know that I want to write all those out and have to circle every time. So let's say, for example, here, let me take you here. Let's say we were looking at, instead of x to the third and x to the fifth, where we said x to the third was what they had in common, what if it was x to the 30th and x to the 50th? Do you want to write out 30 x's and 50 x's and circle what they have in common, or can you see it? Okay, if I have 30 of them here, and I have 50 of them here, how many are we going to be able to circle from both lists? The 30 of them, right? Or if I had 80 here and let's say 70 here, how many would they have in common? Well, they'd have 70 in common. All we need to do for variables is identify the smallest exponent we see. Whatever the smallest exponent is, that's what they're going to have in common. So for example, here, looking at the x's, there are 2 with this term and 1 with this term, so how many do they have in common? They have the 1 in common, right? Or if you're looking at the y's, there's 1 here and then 4 here, so what's the smaller? The 1, that's what they have in common. Okay? So for variables, pretty simple. For variables, you're going to be using the smallest exponent that you see with it. So if you have x's in your terms, look for the smallest exponent on x's. If you have y's, look for the smallest exponent on y's, and so on. Okay? Now let's try to combine those. So let's look at when I say those, I mean numbers and variables now. Okay? See if we can identify the greatest common factor for these two terms. So let's start with the coefficients. What's the biggest number that goes into 5 and 10? Well, that's going to be 5. And how many x's are these two terms going to be having in common? If I have 4 here and 2 here, they're going to have those 2 in common. So 5x squared would be the GCF for those two terms. Okay? If you're feeling alright with this and you want to try the next one out, go for it. Otherwise, let's see, what is the biggest number that's going to divide into 16 and 24? Again, if you're not sure, let's just go in here and type in 16 and 24. Hopefully you knew it was 8, but there it is on technology as well. So 8, and now my screen's weird. Let's go 8, and then how many x's do the two terms have in common? Well, I've got 2 here, but only 1 here, so they have 1 x in common. And then how many y's? Well, there are 3 here, but only 2 here, so we're going to have a y squared in common. So our GCF is going to be 8xy squared. Okay? Hopefully, baby steps, we're feeling alright so far. The goal is not just to be able to find the GCF, it's to be able to remember factor it out. So once we've established what the GCF is, how do we go about factoring that GCF out? So let me go back to our first problem here. Okay? Remember, when we're factoring, we're going to be starting with this and then trying to work backwards. So if I was starting with this as my problem here, 6x to the fourth, 10x to the third, and negative 8x squared. So ignore this for a second. Okay, if that wasn't there, what I would be asking you to do in factoring this is first identify what the GCF is. Okay, what is the GCF for these three terms? Well, the biggest number that divides into 6 and 10 and 8 would be 2. And how many x's do they all have in common? Well, there's 4 here, 3 here, but only 2 here, so they have 2 of those in common. So 2x squared is my GCF, and you see it right here, 2x squared. So once I've established the GCF, I know that that's what's going to go outside of my parentheses. So that goes outside of my parentheses. So all I have left to do now is figure out what goes inside of the parentheses. And it should make sense that because factoring is the opposite of multiplying, that to figure out what goes inside the parentheses, we're going to divide. So 6 divided by 2 is going to give me 3. And remember, our division rule with exponents says to subtract those. If I have 4 x's here, but 2 of them are going to be divided out, then subtracted out, we're going to have 2 left. And I see that occur here. And then 10 divided by 2 gives me a positive 5. And then if I had 3 x's, but I take 2 of them out, I'm going to have 1 left, and I see that here. And then negative 8 divided by 2 makes a negative 4. Those 2 x's get divided out, no x's left, and I see that. And that's it. So I had 3 terms, divided 3 times, got 3 results, and then ended my parentheses. And apparently, lots of dots all over my paper as well. Okay? So that's the process we're looking at. And let me just undo a million times so I don't make my note sheet look all ridiculous. Too many dots. Okay, there it goes. So let's go back here. What is our process for factoring out a GCF? We're going to figure out what the GCF is, so find the GCF, and that GCF goes outside of a set of parentheses, so outside of the parentheses, okay? Now we got to figure out what goes inside of the parentheses, and we do that by dividing. So we're going to divide each term by the GCF, and those results go in the parentheses. And remember, when we're dividing, we're using our dividing rule, our quotient rule, where the dividing happens with the coefficients, and then what we're doing with the exponents is we're subtracting. Okay? And that's it. GCF, divide. Okay, now we could be dividing 3 times, 4 times, whatever, but that's it. And the great news with factoring is you can check your work. If you want to make sure you factored correctly, multiply it back out, and you should get the same polynomial that you started with. So answers can be checked with multiplication, by multiplying. Okay, and then just as a note, all right, the number of terms in the parentheses should always equal the number of terms that you started with. Sometimes, and I'll show you a case where it happens in a little bit, we miss a term. They happen in certain situations, but make sure if you start, like for example, number 6 with 3 terms, that in your parentheses you should have, 3 things going on in there as well. Okay? So let's try this out. Let's see if we can factor. 5x cubed plus 10x squared minus 15x. First, we want the GCF. Biggest number that goes into 5, 10, and 15 is going to be 5. And then we have 3, 2, 1, x in common. So 5x is our GCF. That's going to go outside of our parentheses. And now we want to divide to figure out what goes inside. So 5 divided by 5 is 1. And then if I have 3 x's, but I get rid of 1, I'm going to have 2 left. Now that 1 is optional. If you want to put it there, awesome. If you don't want it to be there, that's okay. That 1 is implied in front of the x squared. Okay? How about the next one? 10 divided by 5 makes a positive 2, so I'm going to put a plus 2 there. And if I had 2 x's, but I divide 1 out, I'm going to have 1 left. Again, putting the 1 on the exponent, that's optional. And then lastly, negative 15 divided by 5 makes a negative 3. And if I started with 1x, but I took it out, no x's left with that term, and then we're done. Okay, so there's my answer. And again, if I wanted to do a quick check, you can just do this in your head. Here's my 5x cubed that I started with. Here's my 10x squared that I had next. And then here's my negative 15x that I had at the end. Boom, factored. We took one polynomial and made it a product of 2. Okay? All right, how about here? Let's try this again. What's the biggest number that goes into 24 and 12? Well, that's going to be 12. And we've got 1x here, 3 there, so 1x in common. And 4y's there, but 1 there, so 1y in common. So GCF is 12xy. We're going to put that outside of our parentheses. And now we're going to divide to figure out what goes in the parentheses. So 24 divided by 12 is going to be 2. And if I get rid of an x and a y, then I won't have any x's left. I'll just have 3 y's left. Okay? Negative 12 divided by 12 is going to be a negative 1. And then I'm going to get rid of an x and a y, so I'm just going to have x squared left, and then we're good. And again, if you don't want this 1 there, that's an optional 1, so it doesn't have to be there. But there it is. And again, you can do a quick check. If I multiplied here, I'd get 24 and an x, and then a y to the 4th. And if I multiplied here, I'd get a negative 12, x cubed, and a y, and that is exactly what I started with, so I confirmed my answer. Okay? And that can be done in your head if you're comfortable doing that in your head. All right, moving right along. Let's look at number 8. What's the GCF here? What's the biggest number that goes into 8, 4, and 2? Definitely 2. Now what about x's? Well, there's 2 x's in the first term, 1 here, so you might be tempted to say x to the first in the GCF. However, if you look at the third term, there aren't any x's here. If if all of the terms don't have an x, you're not going to be able to factor out an x from all of the terms. So that means our GCF here is just going to be the 2. So since there's no x's with the third term, I cannot factor x's out of all of those terms. They don't all have x's in common. So sometimes our GCF is just a number, like 2. So if I just divide each of these terms by 2, then I'll have left 4x squared minus 2x, and then minus 1. And there it is. Not so bad. Okay, so sometimes our GCF is just a number, and then the reverse is going to happen here. Or not the reverse, but something similar happens here. What's the GCF this time? So the biggest number that goes into 3, 5, and 7 is a 1. And if 1's the GCF, and we don't really, I don't want to say we don't count it, but 1 goes into everything. So we're not going to be able to divide, dividing by 1's not going to change anything either. So we don't have to worry about anything other than 1 going into the coefficients. But how many x's do we have in common? 4 here, 3 here, 1 here means all we can take out of these 3 terms, all we can factor out of these 3 terms is an x. So if I just get rid of an x from each of those terms, I'll still have a 3, but now x cubed here. I'll still have a minus 5, but an x squared here. And I'll still have a plus 7 with no x. Okay? So there it is. Sometimes we can only take out a number, sometimes we can only take out a variable. And now that I zoomed in, those look much smaller than the others, but whatever. All right, so here, let's go on in number 10. Biggest number that goes into 2, 4, and 6 is going to be 2. And then I have 2 x's, 1x, 1x, so I can take out an x. Then I've got 2 y's, 1 y, but no y's over here. So I can't take any y's away from these terms. So just a 2 and an x. So 2 divided by 2 is 1. And then I'm going to have 1x left, both y's left. And again, this is going to be an optional 1. And then 4 divided by 2 is going to be 2. And if I get rid of the x, I'll just have the y left. And then negative 6 divided by 2 is going to be negative 3 with no x left. And there we have it. Okay? All right, got one more here for you to try. So give it a shot. If you feel comfortable with it, pause the video. If not, let us continue. Biggest number that goes into 24, 18, and 12 is going to be 6. And we're going to have one a in common. So 24 divided by 6 is 4, with 4 a's left, a to the 4th left. 18 divided by 6 is going to be 3, with an a squared left. And negative 12 divided by 6 is going to be negative 2, with no a's left. And that is our answer. Okay? Now, I said I was going to bring in one of these problems where a term was missing, and I forgot to put one in there. So let me just show you one more thing. Okay? If you had, let's say, 4x squared plus 8x, well, let's do cubed here, plus 8x squared plus 2x. Okay? What's the GCF for these 3 terms? Well, definitely a 2 and an x. So, and actually let me change, I'm going to change this to 2. Okay, so this is what I should have showed you. I should have put one like this in the front, but here it is anyway. So 2 divided by 2 is going to be a 1 here, and if I started with an x cubed and I took one of them out, then I would have an x squared left, right? And then I said this is an optional 1, so we could get rid of that. Or you could leave it either way. And then 8 divided by 2 is going to make 4, and then 2 minus 1 leaves me x to the 1st, and then 2 divided by 2 is going to be 1, and then there's no x's left. So in this term, right here, this last one, I have to keep the 1 here. In this one, the 1 is optional. The 1 could be erased because there are still x's here to hold the place of the 1. But in the last part here, because the x's canceled out and all I have left is the 1 has to be there to hold the place. So there are situations like this where sometimes that gets missed because people are like, oh, it's a 1, I don't need it. But remember, if you start with 3 terms, then you should have 3 results of dividing. You should have 3 left in the parentheses, okay? So it'll be the one spot where you got to be a little bit careful. And we're going to talk more about GCFs in the next topic, and actually we'll see GCFs throughout our factoring processes, so this will be something we get to practice. Although you do have a practice assignment just for this, so go ahead and work on those problems, and if you find yourself struggling a little bit, then reach out.